Hello, everybody. Welcome to my channel, Island Daily. My name is Dr. Eamon, and I'm an optometrist. And today we are going to learn about visual pathway and its lesions. So let's get started. So here's a rough sketch of the visual pathway, and now we are going to add more detail to it. So the rule number one is, let's suppose this one is the right eye and this one's the left eye, right? Right here we have our retina. What you have to remember is that the nasal visual field is going to be made by the temporal retina, and the temporal visual field is going to be made by the nasal retina, and vice versa with the superior and inferior visual fields. The superior visual field is going to be made by the inferior retina, and the inferior visual field is going to be made by the superior retina, right? Now, keeping in that mind, we will take this further. Now, at the level of retina, right over here, there can be three scenarios. Scenario number one is that there can be, now, right here is the macula where the central vision is going to be made. So at the level of retina, there can be central scotoma, right? There can be peripheral visual loss. Also, there can be sectorinopia, right? So a central scotoma is going to look like this. And the reason can be a CSCR, anything, a condystrophy, like anything which is affecting the macula, right? The peripheral visual loss is going to look like this. And this occur in retinitis pigmentosa, right? And sectorinopia can be an area of blindness in any of the peripheral visual field, right? And there can be multiple reasons. There can be a retinal detachment, and so now the fibers, the axons actually from the ganglion cells, are going to make the optic nerve, right? So this portion over right here is the optic nerve, right? At this level, if any of the lesion occurs, there are going to be a complete blindness, right, of the ipsilateral eye. Now what happens is that at optic chiasma, only the nasal fibers are going to decussate, and the temporal fibers are going to stay uncrossed. Now at this point, if any lesion occurs on the very periphery of the optic nerve involving only the temporal fibers of the ipsilateral eye, this is going to cause hemianopia of the ipsilateral eye, and since it is involving the temporal fibers of the left eye, so the right side, the it is going to cause hemianopia of the right side of the ipsilateral eye. So how are we going to document it? We are going to document it like left hemianopia right? Now, if the lesion occurs right at the optic chiasm, so right over here, we know that the nasal fibers of both the eyes are crossing. Now, this will be case number 6. Now, both the eyes are involved, right? And since the nasal fibers are involved, so both the temporal visual fields are going to be affected. And we are going to document as bitemporal hemianopia. Or we can also call it heteronymous hemianopia, right? Now, if the lesion occurs over right here, now what is the space called? This is called the optic tract. This one was the optic chiasm. This right over here is the optic tract, right? Now, the optic tract of the left eye is carrying the visual field of the right side. Now, focus on my words. It is carrying visual field of the right side at the point of from the point of optic tract onwards, the left side will carry the right visual field, and the right side, the right nerve fibers are going to carry the left visual field. Now, how does that happen? Now, at the optic tract, the lesion number 7, the nerve fibers of the left eye and the right. The left temporal fibers are damaging, which means that the left eye nasal fibers are going to get damaged, right? Nasal visual field is going to get damaged, right? And the right side nasal fibers are damaging, which means that the right temporal visual is going to get lost, right? So what does this make? This makes a right homonymous hemianopia. So from here onwards, the left fibers are going to control the right visual field, and the right fibers are going to control the left visual field, right? Now, what is this? This is called the lateral geniculate body. Now, this structure right over here is very interesting. This acts as a relay center, and it has 6 layers. Now, if you make its structure more like this, it has one, two, three, four, five, and six. It has 6 layers, and the layer from 1, 4, and 6 are from the contralateral eye, which means it carries nasal fibers, and 2, 3, 5 are ipsilateral. Ipsilateral means from the same side, and contralateral means from the opposite side. So from the opposite sides are coming the nasal fibers, and the ipsilateral side carries the temporal fibers, right? Now, between these layers, one and wait, let me grab another color. So, right. 1 and 2 are actually magnocellular, and 3 to 4, 5, 6 has parvocellular, right? Also, between, wait, we are going too fast. First, let me tell you what are these magnocellular and parvocellular cells. Magnocellular or M cells or parvocellular or P cells. So the M cells are basically responsible for motion detection, and they carry, and there are actually 5 to 10% in percentage, and parvocellular cells are basically carrying information from the cone cells. Basically, they are carrying midget ganglion cell exons, right? So the information from the parvocellular cells are very precise, and it is responsible for the color perception, the depth perception, right? Between these cells, between these laminas, we have a different type of cell layer, which is called coniocellular cell layer. Wait, right? And coniocellular cells are responsible for blue and yellow color perception, and parvocellular is basically responsible for the major portion of color perception, which is red and green, right? Now, let's say this is a left lateral geniculate body. So any lesion occurring in the first two layers, this will be the case scenario A. Now, any lesion which is occurring in the first two layers will cause a sectorinopia of the right side, sparing the central vision, because the cells from the magnocellular are basically coming from the periphery of the retina, right? So it is going to cause a sectorinopia, sparing the central vision, right? So it is going to cause right sectorinopia, right? Now, if there is any lesion between the layers from 3, 4, 5, and 6, it is going to cause, it is also going to cause a sectorinopia, but involving the central region. The reason, because I've told you before that these fibers are coming straight from the macula, from the cones actually. Not just from the macula, from the cones actually. So it is going to cause a right sectorinopia involving the central vision as well. Now, the fibers will leave the lateral geniculate body and they'll make two loops. This whole portion is called the optic radiation, right? Now, why not we draw it like this, right? So the fibers leaving the lateral geniculate body are going to make are going to call optic radiations, and this in these optic radiations lie two loops. This first one which is extending superiorly. This one right over here is called the Mare's loop. And this right over here going straight is called the Baum's loop. Now, the Mare's loop consists of the inferior retinal fibers, and the Baum's loop consists of the superior retinal fibers. Now, how does it is going to any lesion occurring on the Mare's loop or on the Baum's loop is going to affect the visual field. Now, if a lesion occurs right over here, it is going, since it is carrying the inferior fibers from both the right side and the left side, it is going to cause a quadrantanopia. And since the left Mare's loop is going to be is damaging, it is going to cause a right superior quadrantanopia. So we are going to document it is as right superior quadrantanopia, right? And same goes with this. If any lesion occurs at the Baum's loop of the left side, it is going to cause an inferior quadrantanopia of the right side in both eyes. So we're going to document it as right inferior quadrantanopia, right? We also call it as a pie in the sky and a pie on the floor, right? And what if all all the fibers of the optic radiation gets involved at the same time? So this will cause, if the left optic radiation is getting involved, it is going to cause right homonymous hemianopia, same as the left optic tract lesion. Now, from the optic radiations, these fibers are finally going to get to the occipital lobe, and they're going to lie in the primary visual cortex, which is the Brodmann's area, 17, right? Now, let's just make it even more enhanced. So this area over right here is the primary visual cortex, right? The Brodmann's area 17. And this tiny region carries the central vision, right? So any damage, this one's the left and this one's the right. So any damage which is going to occur at the primary visual cortex area of the left occipital lobe, it is going to cause a right is going to cause a right homonymous hemianopia, sparing macula, right? Now, if an lesion occurs at this very point involving only the central macular area, it is going to cause a right central scotoma, right? Now, uh, I would like to clear one thing that if any physical insult occurs to this area, there is no chance that it's going to spare this area and only involve the peripheral area. Is going to cause a right homonymous hemianopia. But if there is a vascular lesion, it is going to spare macula because the blood supply to this central lesion is different and to the peripheral area is different, right? So this was a whole lecture. I hope I have made everything clear. If you like the video, do like it and subscribe it and do share it with your peers. So that's it for today. Thank you for watching. Goodbye.